So today we're going to continue talking about Morse functions and specifically about handles and handle attachments. So let's remember what we were doing before. So I want to talk about handle attachments. So last time we were looking at, we fixed a Morse function on a manifold with the property that all the critical points, all the critical levels corresponded to a unique critical point. So with the property that the number of critical values, the number of critical points for each critical value was equal to, that the number of critical points of f is equal to the number of critical values. So there is a unique critical value, unique critical point for each critical value. And we also assumed that property about the boundary. So, if the boundary is not empty, then this set of critical points is contained in the interior of x, and the value of x in the interior is strictly less than the maximum of f. And that's equal to the value of f on the boundary. Okay, so that the Morse function, it's like this, if it has a boundary. Okay, but anyway, that just kind of means we don't have to worry about the boundary, really, because if there is a boundary, then it's going to be like above the critical values that we're going to be looking at. And then last time we saw that. So the proposition that we proved last time was that if the interval AB doesn't contain critical values, then the manifolds XA and XB are diffeomorphic. Where remember these, the manifolds XA and XB is the set of everything that's below A. So remember that, recall that XA is the pre-image of minus infinity A. And the same thing for XB. Okay? So this manifold that's everything below A is the same, has the same diffeomorphic type of everything below B if you don't have critical values. So we saw that, we proved this using a gradient-like vector field. And then towards the end of last class, we were looking at what happens when you do cross a critical value. So now, so last time, we were still looking at, so what if A is a critical value? So let A be a critical value. And we can write NP a critical point such that f of p equals A. And what we were discussing last time is how x a plus epsilon can be obtained from x a minus epsilon. And let's go back to what we were doing last time. So last time we looked at a neighborhood of P. So a neighborhood of P, we can use the Morse lemma, and let's say K is the index of P. So that means that there exists a chart around P such that F is equal to, in those coordinates, we can write F like this. So F is equal to A minus the sum of xi squared from 1 to k plus the sum of xi squared from k plus 1 to n. Okay, so we can draw a picture. My picture will be the case k equals 1, n equals 2. But pretty much the same picture is true in general. I mean, it's a little bit more subtle. if k is 0 or n. But basically the picture is kind of always like this. So sort of this is your rk, and this is rn minus k. And when you look at the set where f is equal to a minus epsilon, then you have something like this. So this is like a generalized hyperboloid. So this would be this line. Maybe I should draw with colors. This is the level set a minus epsilon. And then we have a level set a plus epsilon. And basically everything that's, I'm going to write like this. So x a minus epsilon is going to be this part in here. And x a plus epsilon, of course, it contains this part and everything in between. So it's this part here. And what I told you last time, which is not too hard to see, is basically if you look at just the neighborhood of the origin, so maybe you can just look at this neighborhood. I forget what I called it. I think I called it U. And U is the set of points x, y in rk times rn minus k, such that the norm of x times the norm of y is less than delta. Then this is going to be, this U is going to be a set like this. But if you look at the intersection of U with this guy, so when you look at basically in U, so when you look at U intersected with the pre-image of a minus epsilon, a plus epsilon, this is what I was calling last time H. So it's this object here. Well, let me use a different color. What color have I not used? Green. Let's use green. I don't know if you can see. Can you see this green on the blackboard? Yeah. So this is your green. So this is the H. This part right here. And this is really what matters, because away from U, like U is a neighborhood of the critical point. I mean, my critical point P in this chart is just the origin. So U is a neighborhood of this guy. And we know that away from U, the gradient, we have this gradient-like vector field, which you can just pick the gradient or something that looks like the gradient. That'll just go like this, basically. It'll take this, the pre-image of a minus epsilon, except for this neighborhood. So if you remove this part, it'll just be cylindrical. So it'll be kind of this part times minus epsilon epsilon. So we know that when you look at sort of f, this little piece away from U, this is just something, this is diffeomorphic to something times minus epsilon epsilon, by the same argument of the proposition before. And this thing is just, basically whatever doesn't touch this H on F inverse of A minus epsilon. Okay, so you can see it very clearly from this picture, but it's not hard to, write this explicitly. Just using this, you just pick a gradient-like vector field that, in this neighborhood, it'll just do this. It'll just be, sort of minus x and y or something like that. So like the gradient of this thing. So when you exponentiate this guy, it's going to stay tangent here. So it's going to take this boundary point when you remove the h into here. So basically what it is this the pre-image of a minus epsilon minus u minus h. I guess it's the same, removing u. Let's do this. Okay, so it's going to be so when you look at this, what's between a minus epsilon and a plus epsilon that's away from this neighborhood, then you can just use the same gradient-like vector field to show that this thing really is a product of one slice with minus epsilon epsilon. Okay, and here the map is just given by the flow. So this is just, you take x and t, and you take this to phi t of x, where phi t is the flow of a normalized gradient-like vector field. So, by normalized, it's exactly what I did last time. You take a gradient-like vector field and you divide it by f applied to it. Just to make sure that you as you integrate the vector field, the t corresponds to the value, to how much you're changing f. So that at time, and I guess maybe this is 0 and 2 epsilon to be consistent. So you start from here, and then at time 2 epsilon, you get to a plus epsilon. Okay? And just to be completely consistent, you want this vector field to be tangent to the boundary of u here. So maybe in order to do that, you just fix the vector field to be this over here, which you don't know really that's the gradient of the function because you're looking in a Morse chart, and you don't know what the Riemannian metric that you picked really was there. So that's why it's easier to do things with gradient-like vector fields. But anyway, is this diffeomorphism clear? Are there any questions? I'm happy to clarify if there's a question. Okay, so that's the easy part, or the simpler part. And the real interesting part is what's happening here, inside of U. So inside of U, what we have is this H. So this H here, really, it has a very explicit description. H is just, if you want, it has a completely explicit description. It's just a set of points in Rk times Rn minus k, such that the norm of x, maybe we can put, I don't know if I want to put less than or equal to, I don't know. Doesn't really matter. But anyway, let's do it closed. So we have this is less than or equal to delta, and minus x squared plus the norm of y squared is between minus epsilon and epsilon. Okay, and I guess in a way it depends on delta and epsilon, but up to the diffeomorphism, this set is well defined. Okay, so this really is what we call a handle. So this is a K handle. Okay, and the real question is how do we glue a K handle to something to really understand how the topology is changing as we go, through the critical point. And pretty much this picture gives you the description. And I wrote this down last time, but I want to write this down again. So, how do we get x a plus epsilon from x a minus epsilon? So, you can just write the decomposition that you see here. So x a plus epsilon is just sort of x a minus epsilon union. Of course, this is union with the preimage of a minus epsilon and a plus epsilon. And here, I'm not doing disjoint union. I'm gluing along the boundaries here. Okay. So yeah, I'm repeating the level set a minus epsilon, but it's okay. It's glued with some identification here. We can talk about the identification in a little bit, but anyway, how do we decompose this guy? Well, this guy has two parts. It has the trivial part, and it has the interesting part. So this is x a minus epsilon union h, and then union this trivial part, this cylinder. Let's call this, I don't know, t. Trivial not because it's easy, but because it's it's a trivial product. So it's not adding any topology, any interesting topology. Okay, so this is really what it is. Like it's kind of an obvious union. But I guess, to really understand what this is saying, I think to what it means topologically, I think it's best to really collapse this minus epsilon direction. So, this flow, it's well defined on all of T. And it's also well defined on a part of the boundary of H. So you can think that H has, kind of 3 different parts on its boundary. So H, is a manifold, not only with boundary, but with corners. And the corners are basically, when we have equality here and here. So those are what are called the corners. So, I haven't quite defined this, but I won't define it in a lot of detail right now. But maybe I'll do it in a little bit. But, a manifold with corners, topologically, it's a manifold with boundaries. But parts of the boundary, we have these smooth charts that are not taken to sort of a smooth boundary. It's taken to a corner. So basically, like if you look at, for example, a square, this is not, with the inclusion inside of R2, this is not a manifold with it's not a smooth manifold with boundary. It's a smooth manifold with corners, because the inclusion here, basically, this map that takes this guy to this guy like this, it's not a smooth map. So this is, the chart, basically a manifold with corners is going to be sort of a manifold with charts that are modeled on not sort of the half space, but just on the first quadrant of Rn. So, sort of a manifold. I guess I can write this down, kind of. I guess this can even be a definition. A manifold with corners is a topological manifold with boundary endowed with an atlas of charts with values on R greater than or equal to 0 to the n. Okay, so you take the first quadrant of Rn, and your chart can have values there. Of course, this guy is homeomorphic to just the half space, but it's not diffeomorphic. So we can find a homeomorphism that will take sort of this into this, but this map is not a diffeomorphism. So that's why this is actually a meaningful definition. So basically, if you take your manifold like your square, at these points, sort of the chart that we want is really like the inclusion into our R2, or the restriction of the inclusion. And that's going to give it a chart here. That's not really a smooth point, because when you look at the boundary, this will not be a smooth manifold right here. Anyway, so that's a manifold with corners. And what I just gave this definition to say that H is going to be a manifold with corners, and it's kind of simple to see what the corners are. The corners are exactly so. A part of the smooth boundary is going to be if one of these inequalities is an equality. But if you have 2 of them that are equalities, then you actually have a corner and not a smooth part of the boundary. So that corresponds to these points right here. Okay, so H is, so I guess sort of according, H is a manifold with corners. With corners. And what you can see is what is the boundary of H. So sort of the boundary of H is going to have basically 3 pieces. So there's going to be a part which is where we have an equality here. There's a part where we have an equality here. And there's a part where we have an equality here. Okay? So the part when you have an equality here, that is basically the intersection of H with F inverse of A minus epsilon. So there is the intersection of H with F with f inverse of a minus epsilon. That's one part. Then you have another part, which is the same thing for a plus epsilon. And then you have a third part, which is really this part where you're in the interior here, and then this, and you have an equality here. Okay, so this is the union with, say, I'm going to just write like this, x, y in h, such that norm of x, norm of y is equal to delta. So this part here actually belongs to T. It's actually where this trivial part intersects with H. It's exactly this part here. Okay? So, yeah. So this is what it is. But the next step now is to really understand the topology better. What we're going to do is we're going to collapse this direction. So over here, we really have this kind of this vector field, the gradient-like vector field that preserves this part. And we want to take this and we want to quotient it by the flow of this vector field. So we want to quotient it by this R action, or this kind of zero, by this part here. Now this guy here is actually contained, as I told you, in this T. It's the part of H that glues on T. So if you want, kind of how should you see this? So this H is something that you're, so another way to understand this is you take your x a minus epsilon, you take the disjoint union with H, but you glue this, and you take the disjoint union with T, but you glue this in a specific way. So you glue the boundary, so you look at the boundary of H, and then this part here, you identified with the part that's in here. So you glue that over here. And then this part here, you glue with T. And then there's another part of the boundary of T that you also glue to x a minus epsilon. And then there's a new part of the boundary, which is going to be this part here. Okay, so you can see all of this from this picture. So I can kind of say this again. So you start with your x a minus epsilon, which has the boundary, this pink thing. Okay? So you can think, okay, now I can actually do the disjoint union with H and with T. And then how do you glue them? Maybe I'm gonna write this down over here. So you kind of, I really want you to understand this because this is kind of the most crucial point of the construction. So first I wrote these, the disjoint union of three things. First I wrote the union without it being disjoint, like where they overlap. So I can actually describe this in the following way. I can say my x a plus epsilon is, I have the x a minus epsilon, then I take the disjoint union with H, and I take the disjoint union with T, but I have to quotient by something, which is like how I glue these things together. So what is this quotient? So when you look at the boundary of H, I already described it has three pieces. And what's the boundary of T? Well, the boundary of T also has three pieces. So because you have this part here, you have this part here, and you have this part here. So basically the boundary of T, you have sort of the pre-image of a minus epsilon minus u. Then you have union with this, the pre-image of a plus epsilon minus u. And then you have this part here, kind of where it intersects the boundary of u, times 0 to epsilon. And then you have sort of this guy here, intersected with u. Intersected with H. No, sorry. You have, well, I can just write it like this. So it's the set of x, y, such that this guy plus this guy is equal to epsilon, and norm of x, norm of y is equal to delta. so this thing here, times 0 to epsilon. So in this picture, this guy here are these points here. This orange part. And then times 0 to epsilon. Okay, so that's the boundary of T. And then let me write the boundary of H again. So you see, at the boundary of H, I have this guy intersected with H. Then I have this guy intersected with H. And then I have union, a cylindrical part, which is, this set of points x, y in H, such that norm of x, norm of y is equal to delta. Yeah, which if you want, this guy is the same set as this guy. These two are the same. They're exactly, sort of these points here. I mean, here you have points, but in general, this is a product of two spheres. In this case, it happens to be S0 times S0, which is why you have 4 points. But here, yeah, anyway, this is going to be a product of two spheres. It's not too hard to see, if you solve this equation. So anyway, now how do you obtain this xa plus epsilon? You take this disjoint union and then you glue. And how do you glue? Kind of in the obvious way here. So you're going to glue these two parts with the corresponding part on the boundary of xa minus epsilon. And you glue this part with this part. And then these parts here you don't glue. You just let them loose. But the point is that, sort of this is going to be the new boundary. So when you let it loose, these two parts here are going to correspond really to the new boundary. So you see, it's exactly the new boundary is going to be sort of the boundary of the cylindrical part, which is this guy here, which is actually this guy and this guy are actually diffeomorphic. No, sorry. This guy and this guy are actually diffeomorphic. So this part here, is diffeomorphic to this part here. So you glue this part, but then you kind of get it back. Which is kind of what happens here. So when you glue this part here, you get it back here. So it's diffeomorphically the same thing. But the interesting thing is you exchange this part here by this part here. So this is kind of the real thing that's happening on the boundary. And this is actually called surgery. It's a phenomenon that's happening on the boundary. So you exchange this part here by this part here. Okay, this is really what's happening to the topology. So you're exchanging this part. No, sorry. You're exchanging this part here with this part here. So this disappears and this appears. So this is the process that's happening to the boundary. And if you really want to understand what's happening, you need to look at what kind of object this is. So if you do a little bit, it's very simple kind of analytic geometry, like I told you, like analytic geometry on steroids. And you look at these hyperboloids in higher dimensions. It's not very hard to see that this guy, I think I might even have done the calculation last time. This is diffeomorphic to a k minus 1 sphere times a ball n minus k. I think I did do this calculation last time. And this part here is diffeomorphic to a bk times an s n minus k minus 1. So it's a sphere. So the way to remember this is like you have the sphere here in Rk. So this is a sphere. And then you thicken it inside of this hypersurface. So when you thicken it, it's the same as taking the ball with n minus k. So you trade this guy with this guy. So that's really the process that's happening to the smooth topology of the manifolds. Like you remove an sk minus 1 times bn minus k, and you add a bk times sn minus k minus 1 to the boundary of the thing. And in the interior, you add this piece here, which is just the h. So a way to understand this, and that was kind of the last thing I said last time, is you see there's a trivial thing happening here. What we can do is we can quotient this trivial part to really understand better what's happening. So that's what I'm going to do now. So I'm going to quotient basically the t and the h, I'm going to quotient by the action of this vector field. Which just means, like all the points, I'm just going to identify the 0 plus the 0 to epsilon with just a point. So I quotient this part, and when I quotient this, again, it's a little analytic geometry exercise to see what's happening. But it's not very hard to kind of to see what really is happening, which is that what happens is that we're going to have, I want to leave this picture. So if you take that decomposition there, so if now you take your h and you quotient by, let me write it like this. Xy with e to the t, e to the minus tx. Well, let me just say I'm quotienting x by phi t of x. When x is in the complement of u. So when x is in f inverse of a minus epsilon, a plus epsilon, minus u, and I'm going to take the closure because I also want to quotient it like over here. So when I do that, so I actually do that for h and t. So I want to take this equivalence relation. Let me just write it like this. So this is my equivalence relation. And now I can quotient h and t by this. So when I quotient t by that, that's really easy because my t is just a product. And I'm quotienting it by the second term. So this is just going to be, diffeomorphic to the factor that, the other factor. So this guy minus u. I guess I was a little sloppy about whether I wanted u to be open or closed. But, I guess let's just make it closed. So let's just kind of take u closed and just take this closure. Kind of I want to go all the way to this point. I want this overlap here to really have manifolds with corners. Anyway, this is just a subtlety. You see what I'm saying, right? When I remove u, if u is closed, then I take this guy away. But I want to put it back, so that's why I'm putting the closure. Anyway, it's just, I don't want to just be strictly bigger than delta. I want to actually have bigger than or equal to. But anyway, so that's what I obtain. So when you look here, what happens when you quotient what happens to this boundary when you quotient by this action is really like these two guys are identified, on the boundary, and this guy gets collapsed. So really, sort of this part here becomes trivial. Like I'm kind of not doing anything, kind of when I'm collapsing here with t. So t kind of becomes completely irrelevant. Like this t is actually going to become, it becomes part of the boundary of x a minus epsilon. So after I collapse, this guy is already part of this guy. The f inverse of a minus epsilon, which is the boundary of this guy. So really, this trivial part is not doing anything. And what happens is that really, it's just the h that's interesting. And what happens to the h, and here's the exercise, is that this guy, and I don't know if you did it, I asked you to do this last time, but you can actually see that this is diffeomorphic to a product of two disks. So when you collapse this guy, these points here, these corners, So at first it had, sort of two corners. First you have this guy, and then you have this guy, which correspond to taking, this equal to delta, and then this guy equals to minus epsilon, or this guy equals to plus epsilon. That would be like two corners, two corner manifolds. I mean, in this case, it's going to be 2 S0 times S0. But in general, this is actually, these corners are sk minus 1 times Sn minus k minus 1. So these are the corners. But you have two of them at first with the original h. But when you quotient it out, you identify them. So what you end up getting is you just get this guy as a corner. And in this kind of collapsed manifold, this is diffeomorphic to basically what I can call h bar, which is actually a product of bk by bn minus k. And over here, you can see really clearly what the corners are. The corners are really just, the boundary of this times the boundary of this. So this guy here is a manifold with corners. And the corners are basically, the boundary has two parts. And the corners is kind of the intersection of the two parts, or where the two parts meet. Okay, so the corners are really, so the boundary, I guess, of this guy is, the boundary of bk times bn minus k union bk times the boundary of bn minus k. And the corners are where these two meet. Or, I guess the corners, this is the boundary of bk times the boundary of bn minus k. Okay? So, I can write it in terms of sphere. I mean, I guess I don't need to do that. Everybody knows the boundary of a ball is a sphere with dimension, dimension of the ball minus 1. Okay. Well, I guess I can write it. Why not? This is sk minus 1 union bn minus k. No, times, and then union bk times Sn minus k minus 1. And the corners is really, sk minus 1 times Sn minus k minus 1. Okay, so we have a much nicer description. And then what is happening to the topology, at least if you ignore questions of smoothness, just questions of, kind of the differential topology, or, I mean, not the differential, the sort of, the C0 topology, What's happening to the manifold as a topological manifold, what's happening is the following. So you take your, how do you build this guy as a topological manifold? What's happening is you just take the other guy, and now you kind of, the t doesn't do anything. If you take the disjoint union with t and you identify it, you kind of don't do anything. So what you're really doing is you're gluing this h bar. So you're taking the disjoint union with this h bar, and then you're collapsing with some map. And what is the map? It's the map that's going to identify this part here. So remember, this part here corresponded to this part here, which glues on the boundary. So that's what you do. So you just kind of identify. I can say that this part sort of is the negative part of the boundary. So I'm going to call this del negative. And this part here I'm going to call del positive. So what you're doing is you're taking a map that will take a point in del minus to the f inverse of a minus epsilon, so to the boundary of this guy. So this is a map, I don't know, phi. And this is really actually if you want, it's the diffeomorphism this diffeomorphism right here. This is really this map. I actually haven't changed this, but this quotient that I did doesn't do anything with this. It just collapses this part. But it keeps this part and this part intact. But now they glue to each other. On the original h, they don't touch. But after I collapse this part, and now these do touch exactly on the corner. And anyway, this guy here is a part of the boundary of the original guy. So it's a part of f inverse of a minus epsilon. So I glue x a minus epsilon to this handle by just using this diffeomorphism here to glue. And then what happens is I get a new manifold. And this, as a topological manifold, is x a plus epsilon. So I can kind of redraw this picture with the collapse so you can see what's really happening. So if you draw this with the collapse, after you collapse, then really what you have is this. So here's your x a minus epsilon, and then you put your handle here, which is called h bar, which is the product of two balls. And you have two parts of the boundary. So you have this part here. This part here is what I'm calling the negative boundary, the negative part of the boundary. And then you have the positive part, which is this blue part. So what do you do? So you glue this negative part to the boundary of what you had before. So you have this gluing here. And once you glue, then you're going to end up in this picture with something that looks like, this. This is x a plus epsilon. Okay, so now I can even describe what the boundary of this new guy is. So the boundary of this x a plus epsilon, which is the level set at a plus epsilon, is going to be the same as x a minus epsilon, but what do? You remove something that has the type of del minus of h, and you add something that has the type of del plus of h. Okay? So this procedure, actually, what you're doing to the boundary is called a surgery, which is kind of what I described over there. So you have your manifold, and then you remove this guy, and you add this guy. That's what's happening to the boundary. Well, what's happening to the whole manifold is really what I described right there. You take the disjoint union with a product of two disks, where you glue in this way. Like you glue just part of the boundary of the handle. And you glue this part, and you let the other one loose, which is going to be part of the new boundary. Okay, so this is kind of what you obtain after you go through the critical value. So this is really what the procedure is, with one little caveat, which is the question of smoothness. Okay, so what's happening with the smoothness here? You can see that even in these lower dimensions here, this guy here doesn't seem to be smooth. Right, so there's something going on. If you look at the original construction, you end up with something that's smooth. But when you collapse, there's really not a great way. You don't really get a manifold with boundary. You get a smooth manifold with boundary. You get a smooth manifold with corners. So you have to say something about the smoothness. And I don't want to kind of talk about this in a lot of detail, but there's something called smoothing the corner. So when you have a corner, that sort of means that it's not a smooth part of the boundary because it comes with a chart that is not equivalent in the smooth world to sort of a smooth boundary chart, but it's homeomorphic to a smooth boundary chart. So smoothing a corner is changing the atlas of the manifold to make it into a smooth manifold with boundary. So you can always do that basically, because if you have a corner, that means that your chart is. So this is just in 2 dimensions, but it's true in any dimension really. But if a corner is a point that gets taken to a part of the coordinate axis in Rn, where you basically I can write this down, but I don't really want to erase anything. No, I can erase that side. Let me just kind of quickly say what it means to smoothen the corner. The first time I heard this, the professor who was teaching the class was just like, "Oh, you just smooth the corner," and it's kind of obvious, but it's not that obvious what really it means. So maybe it's not obvious for you. So maybe I should say what it means. So if you take a point which is on a corner of a manifold, what does that mean? That means that there exists a chart centered at P that goes into sort of this first quadrant. So there's a chart. And the point is that the image of P is not only on a hyperplane, but on two hyperplanes at the same time. So, for example, it's something like this. So P goes to 0, 0, and then blah, 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 blah. If you just have 1, 0, that means you're like on a smooth part of the boundary. If you have 1, 0, and then everything else is non-zero, that means that your chart is right here. So this is a smooth part of the boundary. But if you have at least 2 zeros, then that means that you're not on a smooth part, you're on a corner part. So that means you're like, for example, here. So in 2 dimensions, you really only have one kind of corner. In higher dimensions, you have more types of corners, because if you are on the first quadrant or octant of R3, then if you're a corner, you could be over here, or you could be over here. And if you are sort of on this plane, then you're on like a regular part of the boundary. Over here, you're at a certain kind of corner, and here in another kind of corner. So these are called the strata of the corners. But I don't want to really talk about this. But the point is that even if you were here, say, or if you're here, what you can do is you can smoothen this corner. How do you smoothen this corner? So you take every chart that's centered around this corner, and you compose with the homeomorphism that takes this guy to this guy. So there's a homeomorphism here. So when you take all the charts and you compose them with this homeomorphism, now this will give you a new atlas, which will make this point a smooth point on the boundary. So you change the atlas, basically, by brute force to make that point a smooth point on the boundary. Okay? That's just what it is. So you define a new smooth structure. Okay, so that's what it is. And you can do that for any kind of corner. Okay, basically because, the neighborhood of any corner is homeomorphic to just, a neighborhood of any boundary point. Okay, so that's the operation of smoothing the corners. So that means, if you look at that picture like this, and you glue your, disk like that, then you have these corners, then the operation will just smoothen them. So we'll transform this into this. That's the smoothing the corners. Não, mudança de carta é não, depois que você compuser com esse cara, vai ser um difeomorfismo. Sim. Mas a mudança de carta agora vai daqui para aqui, né? Por quê? Né? Porque a mudança de carta original, daqui para aqui, é um difeomorfismo. Então, quando você compuser com esse daqui e com outro lá, isso aqui vai ser um difeomorfismo. And that's what it means to be a smooth atlas. You want all the coordinate changes to be diffeomorphisms. Yeah. Anyway, so like schematically, this is what you're doing. But if you really want to be kind of more precise, what you're doing is just really this picture here, like this. If you take this guy, if you kind of cut it here, and you can do it with a formula. I don't want to write down the formula. I think it's better to see the picture. If you kind of find a copy of H bar inside your H, and you look at the original picture, just what you have up to A minus epsilon, you glue this H bar. The smoothing the corners is exactly adding this kind of trivial thing topologically, but that kind of goes between the manifold with corners to the smooth manifold with boundary. So just kind of staring at this picture tells you, kind of really why, when you smoothen the corners, you get what you wanted to get. And if you want to, be really rigorous here, just, look at this local model and write down the equation. And specifically write down, sort of an embedding of H bar inside of H where the negative part of the boundary coincides. And you can really see that smoothing the corners, topologically, it's going to be diffeomorphic to just adding this kind of trivial thing here. Okay? So anyway, this is the procedure of attaching handles. And it's a lot easier, really, to think about adding a handle like this and smoothing the corners than it is to kind of add this more complicated H object and these trivial parts, It just introduces complications that are not necessary when you're trying to describe things. Okay, so I think that now is a good time to do some examples and kind of get our hands dirty with handles. Yeah? Sim. Exatamente isso. And that's exactly what's happening. So if you put the H bar here, and you glue like that, then the figure that you have is this. And smoothing these corners is the same thing as actually, what you get that's what you get from inside this picture here. I mean, this is very easy to see in these dimensions, kind of. In dimension 2, when you add a one handle, that's kind of obvious almost, just from the picture. So in higher dimensions, it's maybe not so obvious. Maybe you have to have some faith here, or you just write the calculation as I'm telling you to do. I mean, it might be helpful to look at this picture in 3 dimensions already, kind of to see what's happening. But there's really nothing mysterious here. The smoothing of the corners is kind of exactly what you think it should be. It's like you see the corner, and it's like you just smoothen it in kind of the most obvious way. You make that into a smooth boundary point. But anyway, yeah, this is what it is. So, I guess you can either think, you can either say, no, this smoothing of the corners, I don't want to think about this, it's too complicated, or I don't know. And you just look at things in terms of topological manifolds in which that there are no corners, a smooth point there's no distinction between corners and no corners. So you don't see a problem there with your glasses that, they just take homeomorphisms as you want. Or you say, no, I want to be, kind of subtle about this, and you understand what really is happening with this smoothing the corners. And it's the same thing that's happening kind of when you go between over here, like between this, the union with this H bar, which you can think of it just being like something inside the H, and what happens when you go all the way along this guy. This is the same, thing, because you can think about sort of, if you have a boundary point, another way to smoothen this, one way you can think about smoothing this, at least in terms of diffeomorphism types, is by adding something like this. So you can think, I'm not going to change the chart, but I'm going to take a union with another manifold with corners, where the kind of corner is going to join with the other corner, and it's going to be in the interior of the manifold. And this new thing now has a smooth boundary. This is another way to think about a kind of manifold, like smoothing the corners. So you can either just change the chart at that point, or you can take the disjoint union with another manifold with corners, where the 2 corners kind of cancel out. Or no, kind of cancel out in the sense that, the 2 charts together make up an interior point. So, if you take a corner like this, and then you take a corner like this, and you glue them, you identify them, then this point here is now like an interior point of the manifold, so you don't have corners anymore. And you can kind of do something like this, and then now this is like really a genuine manifold with a boundary, and with no more corners. So those are kind of 2 different ways to think about it. So you can see that they're equivalent. Maybe that's kind of an exercise. Maybe a little hard to write down, but maybe not so hard to understand. Okay? So anyway, now let's get our hands dirty with handles, and let's see what happens in low dimensions. Well, actually, let me say just one more thing. So what's the procedure again? So how do we attach handles? So you take your manifold with boundary x a minus epsilon. And what you want to do is you want to take the disjoint union with the product of two disks. So, so you're in dimension, so you want to attach a k handle in dimension n. So that means you take your manifold, which is an n manifold with boundary. I guess I can kind of not even say that it's a minus epsilon anymore. I just take an n manifold with boundary. But you think of it, and let's suppose that it's not empty. You think of it really as an x a minus epsilon. So how do you attach a handle? So you take your handle, which is k handle, so that means it's a bk times a bn minus k. And then you have to find a way to glue the handle. And how do you glue a k handle? So you have to find a map that goes from the boundary of bk times bn minus k into, it's actually an embedding, into the boundary of x. So you have to find this kind of guy. There's something in here that's diffeomorphic to this. So that means you find a smooth embedding of this guy into here. Okay? And then now you take your x, disjoint union with h, and you collapse by the map that that identifies x with its image. So kind of this is your x, this is your h, and then you take the map that takes. So this is what I was calling the negative boundary of h. So you have to find a copy of the negative boundary of h inside of the boundary of x. So that's this embedding. So I find a copy of this guy inside here. So here's my embedding. And then I collapse by this map, so I glue. And that's it. So this is the manifold with the handle attached. So this is the manifold with the handle attached. And as I told you, what happens to the boundary of this manifold? So what is the boundary of the new manifold? So what happens is it's the boundary of the old manifold. And then I remove this part, what I'm gluing. So I remove the negative part of the boundary. And then I add the positive part of the boundary. Okay? So this is it. Okay. So I mean, I'm writing not a disjoint union here because there is some identification here. But I don't want to write disjoint union quotient by something because it's kind of obvious what I have to glue. I have to glue along the corners of H. Okay, so that's the procedure. That's the procedure of attaching handles. Okay, any questions about this? Before we get our hands dirty and start to look at what these things mean in different dimensions. I think it's interesting to consider what this is saying for the case k equals 0 and k equals n. Because see that for k equals 0 and k equals n, we have something slightly trivial happening. I mean, it's not trivial, but the picture is a little funny if k equals 0, k equals n, because in our decomposition, we have sort of an R0. So there isn't really decomposition. But remember, I actually considered those cases separately last time. So in the case k equals 0, if you try to interpret this, what is this saying? Well, my handle will be b0 times bn, which is really just bn, because b0 is just a point. It's obviously just bn. And what am I attaching it along? So I'm attaching it along What's the boundary of B0? B0 doesn't have a boundary. B0 is actually a zero-dimensional manifold. Zero-dimensional manifold doesn't have boundary. A boundary would be something of dimension -1, which doesn't exist. So a handle, a zero-dimensional handle, is attached along nothing, along the empty set. So that's, I kind of already said this. That's what happens when you go through an index 0 critical point. It's like a little ball just appears, attached to nothing. It's a new connected component. Like, if you had nothing before, if you had the empty set, then you just have kind of a first little ball that appears. But if you already had some stuff, and you go through an index 0 critical point, then you just have a new ball that appears unattached to anything. Remember, sort of an example like this. If you go through this point, you just have a little ball, and you go through a second index 0 critical point, then you have a new little ball that appears attached to nothing. Okay? And in the case k equals n, it's kind of degenerate in the opposite direction. So what is a handle in the case k equals n? A handle is going to be a bn times b0, which is again another ball. But now it's attached along the boundary of bn times b0. So it's attached along an Sn minus 1 times b0, which is just an Sn minus 1. So that means, if you have an n handle to attach, you must have a part of the boundary that's just a sphere. And you just close it up by putting this ball bn attached to it. And the thing is, what is the positive boundary of this handle? This is actually the empty set. So in this case, the negative part of the boundary is your Sn minus 1, and your positive part is empty. Which is basically, so what that means is, if you have a maximum index critical point, then that means that, right before that, you have a little sphere, and then when you go through that critical value, then you're attaching a little ball, and you're closing it up, and above that, there is no more boundary, at least corresponding to that part of the boundary. So, that means, like, in this construction, there's going to be some sphere on the boundary. So going through an index n critical point, you're going to remove the sphere, and you're going to add the empty set to the boundary. So that's really what's happening to the boundary. Okay? So that's the process of attaching an n handle. And if you really think about it, what I said last time too is that it's the same thing as flipping the Morse function upside down. So if you put a minus sign in front of the Morse function, the index 0 and the index n critical points switch. So this procedure is actually the opposite of this procedure in some way. Like if you put just the ball attached to nothing, the boundary now has the sphere that doesn't interact with the rest of its boundary. And here's the same thing, but flipped upside down. Like, what does it mean to attach an n handle? It means you look for a sphere, and you just cap it off with a ball. Okay? All right, so this is true in any dimension, 0 and n dimensional. But now what I want to do is I want to look at, sort of low dimensions, n equals 1, 2, 3, etc. I mean, of course, n equals 0 is kind of too trivial to even talk about. So let's start with n equals 1. So for n equals 0, we don't really need Morse functions. But n equals 1 is already kind of interesting. So for n equals 1, we have two kinds of handles. So we have 0 handles and 1 handle. So we can have k equals 0 and k equals 1. And I guess we already kind of considered these two here. But let's just see what they are in terms of, just in dimension n equals 1. So in dimension n equals 1, what's a 0 handle? A 0 handle is a b1 times a b0 times b1. So it's just a b1, an interval, attached along the empty set. So that means if I'm looking at my one manifold coming from the bottom up, what I see is just like a little as I go through this index 0 critical point, I just see like a little interval. And I'm going to draw it like this. So this is what happens. Like I could have some other stuff. And then when I go through this critical point, I just kind of have an interval that's attached to it. An interval that's attached to nothing. So I take the disjoint union. So as I go, that means, as I go like this, I just have the disjoint union with a ball of dimension 1, so just an interval. Okay? And when you look at k equals 1, I also get a B1, but I get a B1 attached along an S0. So I should think of it as like an interval, but like this. So I look at, whatever one manifold I have, and I have to find 2 points. So an S0, and then I glue this thing like this. This is what happens when I go through an index 1 critical point. Any questions about this? So this is actually enough to prove the classification of one manifolds. If you just understand these two kinds of handles. Because of the following thing, kind of now, if you want to classify at least compact one manifolds. So classification So, I guess the theorem is every compact one manifold is the disjoint union of circles and intervals, which I'm calling B1 now. Okay, and what's the proof? Oh, just take a Morse function with the properties that we usually require. So let X be a compact one manifold. And let F be a Morse function as usual. As before. So as before, just with the property that there are no critical values on the boundary, and the boundary is kind of the boundary is on the boundary the function attains its maximum, and nowhere else. Okay, so that means you can reconstruct the manifold just using handle attachments. So what does that mean? I'm going to draw the picture, and if you want to fill in the holes later, and write a complete proof, you can do that. But the idea is, you kind of go, you know that it's compact, so you have a finite number of critical points. So you have a finite number of handle attachments. So when you go from the bottom up, you start, of course, with an index 0 critical point. That's the only way to start. So you start with a 0 handle like that. And then, at every step, you can either have a 1 handle or a 0 handle. Which means that at every step, if I have a 1 handle, so let's say that the second step is a 1 handle. So how does a 1 handle attach? So it has to attach to an S0. So if I have a 1 handle now, then there's really there's only one thing I can do, which is there's only one S0 on the boundary. So if I attach a 1 handle now, then I have to do this. And then I'm kind of done with this piece. Then I can't interact with this anymore. This is already a closed manifold with no boundary. There's no more boundary to attach things to. And then I can keep going, and this is one connected component. So this is one thing that can happen. The other thing is like instead of having a one handle, maybe the next critical point is an index 0 critical point, which means that then I have another 0 handle. And remember, the 0 handle just appears attached to nothing. So that means I take the disjoint union of something else. And in this process, I can also kind of elongate this guy like this. And then now it's the same thing, like then what can happen now? I can either have another 0 handle, so I'm going to have another new interval, or I can have a one handle. And if I have a one handle, now there are two possibilities for the one handle, qualitatively. So this new one handle, it can either kind of take these 2 points that are on the same connected component, in which case I'm going to get a circle, or it can connect two different connected components, in which case it will reduce the number of connected components. Okay? So it's kind of easy to continue this process inductively and see that after a finite number of steps, you end up with a disjoint union of things that are either intervals or circles. So maybe some of them close, some of them don't close. The ones that don't close are closed intervals, and the ones that do close are circles. And that's it. Okay? So that's the proof. I mean, I didn't write it down, but maybe it's an interesting exercise for you to write this down. But the idea of the proof is here. Okay, so that's one manifold. Mm-hmm. It's finite. Yeah, because you start with a finite number of handles. I mean, because the manifold is compact. Yeah. So you have a finite number of critical points, so a finite number of handles. So there is a finite number of steps here. So yeah, so it's the disjoint union of finitely many, if you want. Finitely many copies of S1 or B1. And B1. I guess you can have some S1s, some B1s. And then in particular, if you know it's connected, then it's either S1 or B1. Okay. So that's the classification of compact one manifolds. And what about non-compact? Going into the world of non-compact manifolds is a lot, harder in general. But for one-dimensional manifolds, it's actually not so hard. But it's a little harder to do it with Moore's theory because with Moore's theory, you can have like an infinite number of critical points. And then it gets a little trickier to describe that in a finite number of steps. But you can actually prove, in dimension 1 at least, that the only things that can happen are like something that's an open interval, which is the same as R, or something that like has one boundary and then one kind of open interval on top of these. So if you don't require it to be compact, then it can also be this or this. If it's connected. I mean, if it's disconnected, then it can be disjoint unions of these guys. And it has to be countable because it's the manifold is second countable. So if the manifold is disconnected, then it has to have a countable number of connected components. But anyway, I don't want to classify non-compact things. It can be a bigger mess, especially for surfaces already. I'm not going to tell the classification of non-compact surfaces because it can be a lot messier. Okay, but now let's go to dimension 2. So now it's going to start to get interesting. So what happens with n equals 2? So again, so now we have three k values of k to consider. We have k equals 0, k equals 1, and k equals 2. So k equals 0, as in any dimension, like I described there, this is just a little ball that's attached to nothing. So it's just a little ball that will start to exist. So this will just be a B2 attached along the empty set. So, the picture is just you can just draw it like this. So it's It's a little disk that's attached to nothing. So boom, appears. OK, so what about k equals 1? Well, k equals 1, I have a b1 times b1, and it's attached. Remember, you always attach it along the boundary of the first factor times the second factor. So it's attached along the boundary of b1, which is an S0, times a b1. So, you think of your b1 times b1, and you attach it along this part here. So you can think of it kind of as something that coming from a Morse function, as something like this. So you can think of it as like really a handle, like uma alça, like a handle of a purse or a handle of a bag. And that's why it has this name, handle. And you glue like right here. Okay? And then here, for k equals 2, again, it's a b2 attached along an S1. So really, you kind of think of the same picture, but upside down. So you have this disk, and I'm going to kind of have the blue be where you attach. Like that. OK, so now let's play with this and see kind of how you get things. So let's play with these handles. Now I have a handle attachment game. So you always have to start with a 0 handle. Otherwise, that's the only thing that can appear out of nowhere. So you can think of it as the same as like I have some underlying manifold that's there, and then I have a Morse function, and then I see what's happening through the critical values. So that's kind of exploring all the possibilities. So I start with this 0 handle, so that's my disk. And then now I want to attach a 1 handle. So how do I attach a 1 handle? Well, I have to find an embedding of S0 times B1. So what's an embedding of S0 times B1? You can think of it as like an embedding of S0, and then you thicken it. OK, so first we embed at 0. So what's S0? It's just 2 points. So I find 2 points. And then you thicken it. Well, there's only one way to thicken it, except that, so you thicken it. So it looks like there's only one way to glue. But there's one thing that's a little subtle, which is that when you find an embedding of B1 inside of here, there are 2 different embeddings depending on how you orient your B1, really, for each one of them. So sort of you can embed B1 like this, or you can embed B1 like this. And actually, it will give rise to 2 different manifolds after you attach. And I'll draw the 2 pictures so you see, like, either you can kind of glue a handle like this. Here's my handle. I guess you should see it like this. Actually, let me draw a better picture. Let me not thicken it so much, so it's easier to draw. Let's just thicken it a little bit. Or I guess I can thicken it like this. So here is my S0, and then I thicken it like this. So I can put a handle like this. Which means, kind of my interval, my B1, I'm thinking of my B1 here like this, and my B1 here like this. So this is my ball of dimension 1. But if you could also do a different B1. So sort of this, you could thicken it like this, and this one like this. But you could take your B1 like this, and you can take your B1 like this. Which means that what's happening is like, when you look at your B1 times B1, this point is going like this and coming back here, and this point is going like this and coming back here. So the picture that you should have in mind is that you have something like this. Oops. This is what you have. Okay? Let me draw it better, because this is really important. Okay. I don't know if you can see what, my picture is not amazing. Well, sorry, let me do a third attempt at a good picture. Third attempt. If I start here and I end here. No. It's just fourth attempt. Okay, now, there we go. Now you see it. Now it's a perfect picture. Very good. And this is the attaching. So here you go like this, and here you go like this. And maybe you can complain and say, well, there are actually 4 different ways to do this. But really, if you switch 2 of them, then it's kind of the same way. So it's not so hard to convince yourself there are only really 2 meaningful ways to do this, up to isotopy. And then the thing that's interesting is like what happens after you smoothen the corners. Because here you have to smoothen the, I mean, with dimension 1, you didn't have to worry about that. But in dimension 2, you really have these corners. So you have to smoothen them. So after you smoothen these corners, then what you really get is this. See if you can convince yourself that you really get this. The cylinder. So you have 2 connected components of the boundary, just 2 circles. And here, what you get is, can someone tell me what we get here after you smoothen the corners? What is this after I? Exactly. It's a Möbius band. So after you smooth these corners, really, this is just going to go like this with 1 twist. So this is going to be a Möbius strip. Let's see if I can draw this. And then now, you connect this guy to this, and you connect this guy to this. There we go. And this equality sign, it means, like, is equal as a topological manifold, but, with the smoothing the corners in action. And in particular, you see the thing that's cool is like here, you get some surface of boundary, and the boundary has 1 connected component. It's just 1 circle. And here, the boundary has 2 circles. So you see that's kind of what one thing that's interesting that's happening to the boundary is you start with a disk, which has 1 connected component, 1 circle. And then there are 2 ways of gluing 1 handles. You can either glue a 1 handle that's going to split the boundary in 2 pieces, or you can glue a 1 handle that's going to keep the boundary just having 1 connected component. And as you know, this is not orientable. So you start with something that's orientable, and like here, you mess up the orientation. Okay, so that's kind of that's just with 1 handle. So then now, how can we play, Well, now we can either keep adding 1 handles, we can always kind of add a new 0 handle, or we can close it up with a 2 handle. So it's a little bit harder to analyze all the possibilities, but kind of let's play a little bit and see what happens. It's a little harder to classify in the same way, but we'll do that. Maybe not today, we'll do that next time to classifying surfaces, but let's just play with them a little longer. So what can you do now? So now, let's say, you can, for example, put 2 handles. So here, we have a circle on the boundary. So if you can find a circle on the boundary, then you can close it up with a 2 handle. So we can do that here. So if you take this Möbius band, and now with the Möbius band, what you can do is you can attach a 2 handle, which means you glue a disk where you identify the boundary. So boom, you close it up. And then you get a closed manifold with no boundary. Okay, so you close it up, and then you get, I don't know how to draw this, but anyway, you can see, you kind of glue a disk over here. What is that? Do you see what that is? What manifold is that? No? Yeah, it's an RP2. I don't know if you see that or you're just guessing because it's not the Klein bottle. Or can you see that? Você consegue ver que é um RP2? Oi? Yeah. Anyway, maybe you can see it. It's not that hard to see, but it's not extremely easy either. I mean, there are different ways to visualize this, but what I'm claiming is that after you attach a 2 handle here, there's only one way to attach a 2 handle. Once you have the circle, there's just one way to close it up. And the claim is that after you do that, you get an RP2. How can you see that? Well, I mean, one way to see that is you can take your RP2, which is kind of this disk where you identify this part and this part, and you take a point here, and you take a disk, and you remove this disk. It's kind of going backwards. And it's not so hard to see that when you remove this disk, what you have, if you look at a neighborhood of a disk, of a point, what is this guy here? Well, what you can do is you can cut it up like this. This is an annulus. So without the identification, you can cut it up, and you can basically redraw it like this. Kind of, you have the pink and the pink. So you can kind of write it like this. So you have this. Well, this is gray. So I don't know, orange, gray, orange. Or I guess maybe you don't even need this. No, I think it's good to have the gray. So you cut it up like this. You kind of open it, and now you have white, pink, and then you have white, pink, well, let's see. Sorry. Anyway, this is a simple exercise. Now, I don't want to do that right now. But it's not hard to convince yourself that this guy here is a Möbius band. It has one connected component on the boundary, and basically you just have to cut it up in the right way. I didn't prepare this, but I think in 1 or 2 minutes you can figure it out. Maybe it's more instructive if you do it. You just cut it up and you glue it in a nice way. Okay. So anyway, so basically, and now kind of go the other way around. Like an RP2, when you remove a disk, is a Möbius band, which means that if you have a Möbius band and you add a disk along the boundary of the Möbius band, then you get an RP2. Okay, so that's one way to do this. So, then now you can kind of play with this. And you could say, well, so attaching it to a handle kind of kills the game. Now it's the end of the game, so I can't do anything anymore. So I can go one step back and say, well, if I don't add the to handle, what else can I do? So I can take my Möbius band and I can attach another one handle. And again, I have two choices. I can attach a one handle like this, or in a way that's going to break the boundary. And then you see that you kind of have a tree of possibilities that kind of gets more and more complicated. But if you forget the Möbius band for a while, and then just go back here, what can we do with this kind of oriented guy? So, and the reason I'm kind of saying let's stop is like if we try to look at the tree, it's going to get too many possibilities, and it's going to be hard to classify if we don't have a way to simplify. And I'm going to explain how to simplify things next time with like these canceling handles and handle slides. But before that, I kind of want to just play a little bit more just with the orientable guy. So now with the orientable guy, if I want to attach handles, I can always attach kind of an unoriented handle and kind of mess things up. But if I just kind of keep attaching orientable handles, there's only one way to do it once I choose my S0. So if I choose my S0, there's only one way to thicken it up in order that after I attach the handle, I'm still orientable. So when I look over here, basically there's only two ways to attach orientable handles, which is just the two different attachments of S0, like at least in terms of diffeomorphism type. Basically, I can choose the S0s to be 2 points on the same connected component, or I can choose 1 point here and 1 point there. Okay? So if I choose 2 points on the same connected component, what happens is I have another thing that kind of breaks up again. So if I have my guy like this, and I choose my S0 like this, that means I attach a handle like this. So what I obtain is basically, I had my original guy like this, and then I have this guy. My boundary component gets split into two. So I have this. And the other thing that I could have done is I could have chosen my S0 like this, 2 points, and then I attach a handle like this. And now, what I obtain here is something that is like this. So basically, this procedure here, the procedure of attaching a one handle like that, that's connecting two different connected components, is the same as what's called the pair of pants. Kind of adding the one handle like that is the same as gluing it like this, gluing this object to this cylinder. So basically, if you're trying to glue one handles, orientable one handles to orientable surfaces, then basically what you're always doing is you're either attaching, like gluing a manifold like this, or you're gluing a manifold like this, either this or this, and so on and so forth. So if you're just staying in the world of orientable manifolds, I guess it's not so hard to classify them now just knowing this. In a similar way to basically the classification of one manifolds. So basically, let me say this again. The real diversity, like the real wealth of two manifolds, of surfaces, comes from the one handles. Because the zero handles and the two handles are kind of trivial. So the zero handles are always these like little disks that you put attached to nothing. And then the one handles really correspond to either you're taking a connected sum or a boundary connected sum with this or with this, depending on whether the S0 that you're picking to attach your handle is connecting points that are on the same connected component of the boundary or on different connected components of the boundary. So if it's on the same connected component of the boundary, then you're doing this. You're breaking up the boundary. If it's on different connected components of the boundary, then you're doing this. You're gluing the two parts of the boundary. And then now it's kind of it's a tree again, but it's much easier than when you deal with non-orientable. So kind of it's a tree, but it's a controlled tree of possibilities. So what happens now is, we start with your zero handle, and then you glue these things. And sometimes you have a two handle, but a two handle, what it does is just kind of caps this, or caps this. So if you cap this guy, one of these guys, then it's the same as doing nothing. So if you have a one handle like this, and you attach a two handle like that, that's the same as just having a cylinder, which is basically doing nothing to the topology. But if you have a handle like this, and you cap, then you're done with this piece. Then you can't do anything else here. Okay? And then now if you want, now you can just think of this as not a very easy exercise, but at least it's maybe not so hard to convince yourself of all the possibilities that you can get in terms of orientable surfaces with no boundary. That basically all you can have is things like this. Or maybe, something with a lot of holes. And then you close it up eventually. It's not completely straightforward because you could have, configurations that get kind of complicated. So you can have like a bunch of one handles that are like opening up, and then you can kind of close up. There are many different ways you can imagine that this can go. But you can have, you could start with a zero handle, and then you can put a one handle like this, and then you can put another one handle like this, and then, you can put another one handle like this, and then, you can think about a lot of different ways. Then you can put a two handle like this, then you can put a two handle like this, I don't know. And then you can close it up with a two handle like, we can have another two handle like this. No, sorry, I want another one handle like that. And then you can close with a two handle on top. It's not completely obvious to see that this is, a manifold with genus 3. This is diffeomorphic to this. No. No, that's right. Genus 3. That's right. Yeah. You have three holes. You have one here, and one here. Yeah. 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 But it's not completely obvious that you have a diffeomorphism like this. But maybe it's not so hard to see. At least to look at the two pictures and see that you have three holes that are they look independent. And as I said, next time I'm going to talk about an operation with handles that's going to allow us to classify surfaces more easily. That's called handle attachments. So basically I'm going to say, you can actually always suppose that the handles are being attached like this. So first you have something like this, and then you have something like this. And then you have something like this, and then you have something like this. And if this is really true, then it's kind of obvious that you can only get this. If you always kind of open up and close up, open up and close up, and you never go beyond two connected components. And you have a unique zero handle and a unique two handle. And of course, that's not obvious. That's not true if you just start with any Morse function. If I start with any Morse function, I could even have several zero handles and several two handles. Okay? That's why I'm saying, first we're having fun with them. And then next time we're going to kind of really classify. But for one manifold, it's so simple that we can just classify. For two manifolds, it's a little bit more subtle. Okay, so instead of classifying two manifolds, I'll save that for next time. And now I want to talk about handles in 3 and 4 dimensions. Okay, and again, we're going to play with them a little bit in 3 dimensions, at least in 3 dimensions. Yeah, so let's do that. So in 3 dimensions, we're going to have 4 kinds of handles. So we have, k equals 0, k equals 1, k equals 2, and k equals 3. I mean, topologically, obviously, every handle is just an n-dimensional ball. But the real thing is how we divide up the boundary of this ball. Because, homeomorphically, if you take a product of a ball with a ball, that's just a ball of dimension n. A k ball and an n minus k ball, that's just homeomorphic to a ball of dimension n. But the real interesting thing is how we're splitting the boundary of this ball. That's really what makes it a k handle. So, here, we start with a ball, a B3, that's attached to nothing. So, it's just a B3. For k equals 1, what we have is we have a B1 times a B2. That's attached along S0 times B2. And now it starts to get a little hard to really draw with this kind of, in the way that I was drawing, because now if you want to think of the Morse function as a map into R, and you have your manifold embedded into Euclidean space, then you can't do that in R3 anymore in general. You kind of would need a higher dimension to kind of be able to project. So, I'm going to stop drawing it like this, because it doesn't have a lot of meaning. So really what we have is you have a cylinder. So you have a B1 times B2 that's attached along here. Okay, so I'm kind of drawing the attaching part in blue. Okay, I hope you can see it online. This is blue. This is the attaching. Maybe I'm going to choose a different color. Let me draw the attaching thing with pink. I think that's more, it's easier to see. So I have this thing, and then I'm attaching on the pink. So this is the attaching. And here's my handle. Okay, for k equals 2, it looks the same, but it's a B2 times B1 that's attached along S1 times B1. So maybe I'm going to draw the picture like this. I have an B2 times B1, and then, but now my attaching set is this boundary here. So you see, it looks pretty similar. If I could even take this cylinder and put it like this, horizontally. But you see that I'm attaching on different parts. So really, a one handle and a two handle, they look very similar in dimension 3. They're just cylinders, B1 times B2. But what really changes is where you attach. And I'm going to do some examples in a little bit so you kind of see this in action. Okay? And then, of course, a 3-handle is simple. It's just a ball, but now you attach to the whole boundary of the ball. Okay, so let's do some examples to see what's happening. And I'm not going to try to classify 3 manifolds quite yet. Next time, we're going to kind of classify them. I mean, not as nicely as 2 manifolds, but we're going to describe them all. But we're going to need some cancellation theorems to be able to do that properly. But now let's just play. So let's say we start with a 0 handle. And then we want to glue a 3 handle. So what's that? That can be done. You start with a 0 handle. That's just a ball that's attached to nothing. And what's the boundary of that? That's a sphere, which means that I can cap the sphere with a 3 handle. So that means I have my ball, and I can glue another ball where I identify just the boundaries. So you can think about it like this. So I have 2 balls, And I take the disjoint union, and I quotient by the map that the identity on the boundary. Okay, so the map that takes S2 to S2. So what manifold is this? Can you see? Não. O toro sólido não é uma realidade fechada, né? Yeah, so when I do this, the resulting thing doesn't have boundary anymore because I killed the boundary with this boundary. Oi? Seria. É. Seria não, é. This will be an S3. Why? I mean, there are a couple of ways to think this. You can think about this in the following way. So you have your sphere. It has a northern hemisphere and a southern hemisphere. And the two hemispheres are just balls, three-dimensional balls. And they're glued along the equator, which is a sphere. It's the boundary of the ball. That's one way to think about it. But I think another way, which I like more, is to think about the stereographic projection. So when you think about the sphere, after the stereographic projection, so you remove a point, and then you get all of R3. So you can think about a ball inside of R3, and the stereographic projection basically tells you that the complement of this ball is a punctured ball also. So when you look at this, this is your R3, and you look at your R3 inside of S3, one of the balls, kind of corresponds. I mean, it's basically the same thing, but one of them corresponds to one of the hemispheres, and the complement of the ball corresponds to the other hemisphere minus a point. So you can see it this way, like sort of one ball is sort of is what's inside a sphere, what's bounded by the sphere in S3, by this S2 in R3. And then the other ball is bounded by the sphere, but on the other side. So the complement of the sphere, the complement of this ball, so everything that's lying outside of the sphere, plus a point at infinity is another ball. So that's a way to think about this. Okay? So yeah. So there we go. So that's what happens. And actually, this is exactly the handle decomposition that you obtain from the trivial function on the sphere. So there's a trivial Morse function on S3, which will just, if you think about S3 as contained in R4, and you just take any coordinate, any projection, take x1, x2, x3, x4, to, say, x4, that will have exactly two critical points, a minimum and a maximum. And the Morse and the handle decomposition induced from this is exactly this one, with one index 0 and one index 3. Okay, so now, I guess the kind of interesting thing is now to play with one handles and two handles. So let's just add one handle, a one handle. So if I add a one handle, so if I start with my 0 handle, which is this ball, and then I add a one handle. So how do I add a one handle? Well, I have to choose an S0. Let me choose pink. I have to thicken my S0. And sorry, I should say one more thing. To get this the right way, I think what you really want to do is you want to take a map that changes the orientation of S2. So not the identity, but maybe the reflection or something. A map that changes the orientation. Okay. Otherwise, you get something that's non-orientable. That's a little more complicated. Anyway. Yeah. Anyway, when you look at here attaching a one handle, Again, there's an issue of orientation, but like the thing that's orientable, there's only one way to do that if you choose 2 points, which is just to glue one handle like this. And now, it looks like a handle also, like an alça, But now it's a thick handle. But it's still kind of a handle. Instead of being a handle like this, now it's a thick and kind of round handle that you can grab. So this is a 3-dimensional one handle. And so what is this object when you attach one handle? This is what's called a solid torus. So it looks like a torus, but it actually has all this interior in there too. It's not just a shell, but it's a 3-dimensional thing with boundary. Okay? So that's what happens when you attach a one handle in an oriented way to a 0 handle. Okay? And okay, so now it kind of you put one, and now you could put a lot of them. So if you just kind of keep adding one handles, what you obtain, if you add a bunch of one handles, is you obtain what's usually called a handle body, which looks like a genus G surface, but it's filled in. So it's a genus G surface with the interior. So it's a 3-dimensional manifold. It's the 3-manifold that is bounded by the genus G surface with kind of the obvious embedding into R3. Okay? So that's what you obtain when you add a bunch of one handles in an oriented way. If you start doing non-orientable things, then it's more complicated. But in the oriented world, there's really only one way to do this, up to isotopy. Of course, you can already start to see some interesting things could happen. Like, what if I attach the handle like this, like in the middle of this handle like this? Would I get something different than just kind of putting another handle here? And the answer is no. You get the same thing. But anyway, to really talk about this, you need to talk about kind of processes of going, these handle slides and isotopies and stuff, which I will do tomorrow. Okay, but anyway, let's just kind of go back here and see, like now, say I want to attach a 2 handle. I mean, you see, I can't attach a 3 handle to this because to attach a 3 handle, I have to find a sphere. So you don't see any spheres here on the boundary. The boundary here is a torus. There's no sphere in the torus. So you can't just close it up with 1 3 handle. You need at least 1 2 handle to close it up. So can you see how to attach a 2 handle here? How do I attach a 2 handle? You can think of it the following way. You can really just think about this part here. You have to find this sphere, and then you thicken it. So you really have to look for a sphere here on this boundary, and then you thicken it. So I mean, there are a few different ways to do it, but I guess there are 2 ways that seem that will actually get you directly to something whose boundary will be a sphere. So basically, there are 2 circles up to isotopy that you could choose. You could choose this circle like this, or you can choose a circle like this. I mean, there are other things you can do, but the 2 kind of easiest things you can do are these 2. And I'm just going to finish by saying kind of what happens in these 2 cases. So if you choose a circle like this, now I have to thicken it. So you thicken it like this, times the D1. And then you have to attach a 2 handle along this. So it's kind of like you put a lid. So you want to kind of you're going to close this hole with a cylinder like this, and you're going to glue this boundary here of the cylinder right here. So it's like you really put a lid, like it's uma tampinha really to kind of close this hole. When you do this gluing, what do you get? After you smoothen the corners, you actually get a ball again. So you see what's happening? Like when you put this 2 handle here in this way, then you close up the hole, and you go back to a ball. So in a way, you're kind of doing nothing. So you're adding a 1 handle, and then you're adding a 2 handle, and topologically, it's like you didn't do anything. You just kind of had your zero handle. So this is like what we're going to talk about next time, which is something called canceling handles. So this handle is, and these two in this handle are canceling. After you put in this, you actually go back. So when you do this plus this, what you actually go back is you go back to something that is just a ball. You can do that, and then at the end you have a ball. You just kind of fill it up. You just put another ball, and you get an S3. So you can do that. And in this case, kind of, you didn't need to do one handle and two handle, like in terms of the manifold. You might as well just have closed it with a sphere. So this guy is actually a little bit more interesting. Because what happens here? So this, this is actually more interesting. So what happens here is that, you're going to actually want to glue your cylinder like this. So kind of what you want to do is you want to take this and you want to glue a cylinder along these guys here. So what you're doing is like, so you're gluing this cylinder to this cylinder. So the question is like, what do you obtain after you glue this? And what you obtain, it's maybe a little hard to see, but kind of what's happening is like for each slice here, you have a two-dimensional disk in here, in the solid torus, and you're gluing it to another two-dimensional disk along this boundary of the disk. So for each slice here, you're gluing a disk to another disk along the boundary. So what's a disk with glued to a disk along the boundary? That's a two-sphere. Right? When I glue this guy to this guy along the boundary, I get an S2. So what happens is like on this little interval where I glue these two things, I actually get an S2 for each slice. So over here, what I do is I get an S2 times an interval in this little, where I glue this thing. And what happens is maybe not so obvious, but it's not very hard to see, that kind of the complement of when you look at the boundary, what actually happens is now I have a sphere. So when I look at the boundary here, and then with what's left here, I actually have an S2. And when I glue a ball to kind of cap off this S2, what I actually get is I basically get something that's diffeomorphic to an S2 times S1. So maybe this requires a little imagination. And I can try to explain this again next time. We kind of ran out of time. But here, what you really get is you get an S2 times S1. So that's what you get. And the last thing I'll say is that you can think of different yellow curves here. And there's a bunch of yellow curves here. Up to isotopy, there are many of them. And what happens is like you actually you get all the lens spaces depending on which curve you get. So if you take a curve that is like basically a closed curve on your torus, then you're going to get a lens space when you do this construction. But you have to be a little subtle, and I'll try to explain this next time. And just to say one last thing is next time tomorrow, we'll have the class in the morning, and in the afternoon, we won't have a class. I'll just be on Google Meet to take any questions, any final questions for the exam and just in general. Okay, so one more class tomorrow, and then on Monday I can also be available to answer questions here or on Google Meet, or we'll see how it goes. Okay, see you tomorrow.